Lab1 Constant Velocity. The purpose of this lab was to observe the motion of an object moving in one direction at a constant speed. The main principle we were trying to observe was Newton's second law, which states that the net force is directly equal to the rate of change of an object's momentum. Here on this model, we can see a brief preview that in both the predicted model and the observed model, that position versus time has a fairly linear relationship. Our system here was a battery, and our surroundings were the counter that it was rolling on, gravity, and friction. Some initial conditions in our experiment: we started the battery off at the beginning of a meter stick, so the initial position was 0 meters. The initial velocity was a push given to the battery by one of my lab partners, so this was intended to only be in the x direction, but due to human error, there was some also in the y direction. Through some math we talked about later, the estimated VI is only in the x direction for 0.12 meters per second, and the mass of the battery is 0.0115 kilograms. Our experiment, we started out by picking out an object to roll, which was a battery. We then picked our coordinate system. We decided on rolling the battery parallel to a meter stick, and they were both lying on the same counter. We put our battery at 0 meters. Then we pushed the battery forward, trying to be as parallel to the meter stick as we could, but because of human error, it was not rolled perfectly straight. Simultaneously, we started recording at this time. We then uploaded our video to the tracker app. We had the meter stick, so that way tracker would have something to scale to and get an accurate position from, and then we added our coordinate system with positive x being to the right. We then used Tracker app to tell us our observed position versus time by stopping it at different frames and clicking where the battery was on the video to update the position at a certain time. We then used the information given back to us by the Tracker app to input into our GlowScript code to get our predicted position versus time and our predicted velocity versus time. On a related note, we can see on this y position graph that it is not straight. It's not a straight line at 0 meters, so that means that there was some human error in pushing the battery perfectly straight. Here's a snippet of my code from GlowScript that was used to get the data of the predicted velocity versus time graph. In this code, it says the ball, but for our purposes, ball just symbolizes an object that rolled, so ours in reality was a battery. I started by updating the object's mass, then I updated the initial position, then I updated the initial velocity in ball.velocity with an average velocity that I got by getting the change in the initial position and final position and dividing it by the change in time from the beginning to the end. Because in theory, because of Newton's second law, the velocity should be constant the whole time, so that's why I took the average velocity to try and predict better end results. Then I updated the started time to 0.2 seconds, and then I updated the delta time to 0.03 seconds. Then I changed the line of ball.velocity equals ball.velocity plus fnet times delta t to update the new velocity of the ball based on Newton's second law. Here's the output of my code. Some differences and similarities. Here we can see that in the predicted model that the predicted curve of the relationship was a line, and thus the relationship was linear, which mathematically means that the change in position compared to the change in time was constant. This means that the velocity was constant, which this makes sense with the momentum principle. The observed position versus time was mostly linear, but also a bit curved. It constantly was moving in the x direction, just like in the predicted graph, but in reality, the battery also rolled some in the y direction because of human error, which explains why it was different than the predicted data. Other discrepancies are most likely due to the fact that in the predicted model, it doesn't take into account a surface with friction or gravity, which both existed in our observed version of this. But considering this is a mostly linear curve, we can see that it also proves Newton's second law of constant velocity. Some additional questions: if we were to have switched the positive x and the negative x directions in our coordinate system, the only thing that would have changed is that it would be a negative slope instead of a positive slope, because time would still be positive, and the curve would still mostly be linear. So what does this mean? Considering we know all of the system and surroundings, it is possible to know how many forces are acting on the battery. In our case, it was gravity, friction, and our push force. Because of Newton's second law, we know that these three forces added together for a constant velocity to happen, that they must add together to be 0 newtons. And since the velocity was constant, there was no changes in the forces. Thank you.